So good morning, my honors physics class. For you guys, it's Monday morning. For me, it's actually Friday afternoon at 4 o'clock. So I'm kind of sitting here talking to myself in my room. Hopefully nobody walks by and goes, wow, yeah, Burkham's kind of lost it. It'll work. I'll work out. So hopefully I am safe and sound in Washington, D.C. and not stuck in Chicago O'Hare Airport. So hopefully my position time graph has moved me from Wichita to Chicago, Chicago to DC, this being the reference point. I'm going to call that positive displacement. Okay, so let's talk about the assignment that I gave you all on Friday. So there's two main components. So the first one we talked about, where you're going to have vertical motion and you're swinging the rubber stopper around like this in a vertical plane. So you're going to look at two extremes. You're going to look what's going to happen at the bottom, you're going to look what's going to happen at the top. So at the top, your total force, and that's what you are going to feel. If you are the rubber stopper, what are you going to experience? That's going to be force centripetal minus Fg, okay? Now that's just going to be mv squared over r minus mg, okay? So when you get to problem number one, you're given the velocity, you're given the mass, you can figure out the centripetal force, you can figure out the gravitational force. If you're on an inside loop, like a string, or you're driving a car like a roller coaster, as long as this force total is greater than or equal to 0, you're going to complete the loop. Now, at the bottom, you're going to add them together, which is Fc plus Fg. Now, here's the significance of this. Even if this rubber stopper is just sitting here, no centripetal motion whatsoever, you're at least going to feel 1 Fg, okay? Because remember, the force total is what you feel. So right now, assuming that things haven't changed and this room isn't moving, if it is, call me. It's going to be really weird. There's going to be a whole number of other issues. So, Devin Wynn, is the room moving? Okay, good. All right, let's check it. If it is, get in touch with me. So, but if it does start to move, okay, and you're going around like this, you're going to feel heaviest at the bottom because you have to overcome two things, gravitational force, and you have to provide the centripetal force to make it move in a circle. Okay, we got that. So, on part B where it says, is this thing going fast enough? Let me give you a hint, it is. So you could calculate the total force at the top, subtract those out, you get a positive number. You could calculate the centripetal acceleration using v squared over r. And if that number is greater than 9.8 meters per second squared, you'll complete the loop. If you look at calculating the minimum velocity using the square root of GERD, if you calculate the minimum velocity, you'll see that by moving at 4 meters per second, it's going faster than the minimum velocity. So there's a couple of ways you can do that. When you get to number 2, okay, so when you get to number 2, a couple of things. You got to find the mass of the object. You're given the fact that it weighs 800 newtons. You got to find the mass, not a big deal, divide by g. Then what you want to find is the total force. So on number 2, that answer should be something times 10 to the third, okay? Now when you get to number 3, you've got a car going up over the top of a ramp. Now remember, this car wants to go in a straight path. So you're going up over the top of the hill. So you're going to go force total equals Fc minus Fg. Now in this situation, you actually should get a negative number. Don't flip out and go, oh man, that's bad. It's cool. All that means is that you're still going to go over the top of the hill because the road is in the way, so that's going to keep you from falling. Now, when you get to number 4, since you're going to be talking at the top of this loop, you're going to start off and you're going to go, okay, force total equals force centripetal minus Fg, which is going to be mv squared over r minus mg. Now, here's the kicker. This total force is going to be a multiple of your force weight. So initially, you're going to have 0 Fg. You're going to be in a state of weightlessness, just like you saw in the video with the vomit comment, okay? You will be in a momentary state of weightlessness. Now, so your answer to A should be around 16 meters per second. Okay, a little bit less than that. Should be something around 16. So if you solve this, you move this over, you get mg, you get mv squared over r, masses cancel out, v equals the square root of g. That's your minimum velocity to complete the loop. That puts you in a state of weightlessness. Now, that's a minimum. So on B, you want to feel 1/4 your force weight. So in other words, if you normally weigh 100 pounds, you want to be in a situation where you're going to weigh 25 pounds. So over here, you're going to put 1/4 Fg, which is going to be 1/4 mg, and then mv squared over r minus mg. So here's the recurring theme. The mass is going to cancel out. You're going to move this over here, and you're going to get 5 force when you take 1 plus 1/4. G equals v squared over r. Multiply by r. You get 5 force gur. The square root of that is going to equal your velocity. So what you should see, your answer to B should be something very close to your age. Okay, a little bit bigger than your answer to A. Hopefully that makes sense. Oh, A got you the minimum. B is going to get you a velocity where you're going fast enough that you begin to feel something. You're going to feel 1/4 your force weight. So what's going to happen on C, the only thing that changes on C is that instead of having 1/4, you're going to feel 1/2. When you get to D, instead of 1/2, you're going to put 3/4. So what you should see on number 4, your answers from A to D should range roughly from about 16, which is that answer to A, up to about 21, which is your answer to D. So over here, you're going to draw the graph, and you're going to put Fg here, 0, 1/4, up to 3/4, and you should see this graph goes something like this, which again, hopefully makes sense. The faster you're going, okay, so if I model this, so if I swing this fairly slowly, okay, there's not a lot of tension. So the faster I go, if you're at the top of that, the more you're going to feel because you're going to be going faster and faster and faster. When you get to number 5, that's swinging this bucket, you're just going to use, on number 5, since it's the minimum velocity, you're just going to use the square root of gur. Pretty simple. When you get to number 7, or excuse me, number 6. So number 6, you're a fighter pilot, okay? And you're going into the bottom of this flight. Now, you're at the bottom, okay? Remember, at the bottom, force centripetal plus Fg equals what you feel, okay? So you're told that you want to feel 9. If you get more than 9, you're going to pass out. So this needs to be 9 Fgs. Move an Fg over, there's your centripetal force. So your answer to number 6 should be something times 10 to the 4th, okay? So your answer to number 10, something times 10 to the 4th meters, which would be about a 2 mile radius, okay? Pretty good size, but you're in a fighter jet too, okay? All right. When you get to number 7, here's Bubba in the barrel, okay? So this is this one where you're going to be like this, okay? And this thing is spinning around. So you've got gravity trying to make this thing slide down, and friction is going to be acting upward to prevent that from happening. So gravity's trying to slide it down. Imagine me holding this thing. You have friction in the opposite direction acting up. So what you want to do on number 8. So on number 8, you want to start with the idea that mu equals G over AC. And that's the idea that when this thing is spinning, you have the centripetal force going like this, you have the frictional force acting up, you have the gravitational force acting down. So this is technically your Fg, which is going to be mg, and then your normal force, which is going to be acting at right angles to the wall, is what's created by your centripetal force. So that's mass AC. That's why those masses cancel out. So I gave you mu. Hopefully you know what g is. Find your centripetal acceleration. So that centripetal acceleration that you're going to find should be in the mid-60s, okay? So that centripetal acceleration is in the mid-60s. So now, then you want to go, oh, centripetal acceleration equals 4 pi squared r over t squared. So you're going to take that centripetal acceleration, put that in there. Find the radius. Now, be careful about what you're going to use for period, okay? Just give that a little bit of thought. That's all I'm saying. Just give that a little bit of thought, because that has to be seconds per revolution, not revolutions per second. So your answer to number 8, that radius, should be between 5 and 10. So your answer to number 8 should be between 5 and 10 meters. Now, when you get to number 9, here's this wind turbine, okay? Kind of relevant to Kansas. We got a lot of wind. We're going to generate electricity by harnessing the kinetic energy of the wind. So you're going to go V equals 2 pi r over t. You got to find the period. You're told that it's making a certain number of revolutions per minute. Find the period. You know the radius. Boom, there you go. So your answer to number 9A should be around 90 meters per second. Now, that's Hall and Mail. 90 meters per second roughly is about a third the speed of sound. Okay? No, more like a fourth the speed of sound. It's about a fourth the speed of sound. So the end of that tip, because of the fact that it's so long, okay, the interior hub isn't moving that fast. But if you're way out there on the tip of that, you're going to be moving really, 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 really fast. And that's going to be Hall in the Mail. So that's going to be going around like this, and so you're going to be moving really, really fast. Now, when you get to B, obviously these blades have a lot of mass. They have a lot of inertia. They want to move in a straight line. So on number 9, part B, you're going to use centripetal force equals mass times 4 pi squared r over t squared. Okay? Now, the radius, what we're going to do is we're going to treat this blade like all of the mass is located in the center, 19 meters away. Okay? So you're going to use 19 meters as the radius. You know the mass. Use the period that you already found up above, because no matter where you are on that blade as it rotates around, every point on there is going to take the same amount of time to complete one revolution. So your answer to 9B should be something times 10 to the 6th. Okay, that should answer all of those questions. You all know the drill. If anybody has really any specific questions, you can either wait till I get back on Wednesday, or you can email me, but hopefully that kind of covered all of that you need for that. So I'm going to stop this and take a break, get that handed in, and then we'll stop this and we'll start it back up in just a second, and we'll talk about the motions of the stars. So at the end of the class, you're going to be given this packet of lecture notes, and this takes us all the way through everything you're going to need to know about gravity and motions of satellites. So the front page, and this is what I'm going to talk about right quick, is going to be the summary of Kepler's laws of motion. So to really understand Kepler's laws of motion, we need to look at this historically. So if you look at some of the big debates that happen in all of science and things that we screwed up along the way, and that's what type of solar system do we live in? And there's two kind of arguing thoughts, two different perspectives. One is a geocentric model, okay? Geocentric means Earth-centered. And then you have heliocentric, which means sun-centered, okay? That was a big debate for a long time. So there's a couple of advantages of the geocentric model. Number one, it makes sense based upon observations, okay? Now, you all say, if I said, hey, what type of solar system do we live in? You would all say, oh, we live in heliocentric, where the sun is the center, we're the third rock from our star, we go around, all the planets go around. Everybody would agree with that. So, okay, fine, cool, I'll give you that. But I said, let's look at observations, okay? I said, okay, when I get back, we're not going to do this, but hypothetically, let's say, all right, hey, Burkamp has returned. We're going to meet him with a breakfast out in the parking lot Wednesday morning. It's going to be cool. We'll have breakfast. Okay. Then we're actually going to, this is going to turn into a whole day-long celebration. Okay. So we're going to be out there with pancakes, eggs, sausage, whole thing, right? And we're going to see this bright ball of light appear on the eastern horizon. Sun is rising. Okay? Everybody, woo! Okay? It's going to be cool. Emma Lynn's going to be going, ah, look, it's the sun, right? Okay, right? Bailey's going to be going, okay, nice, all right? So we're going to see this thing come up, right? And I'm going to say, what do you see? Oh, right, we see the sun move across. Okay. So we're going to stay out there. We'll look at it throughout the day. At noon, we're going to have lunch, okay? Maybe have sandwiches brought in. And that ball of light is going to be directly overhead at noon. And we're going to celebrate all the way through the day. Evening, the sun's going to set. We'll throw some shrimp on the barbie, have some steaks. It'll be a good time. Sun's going to set. I want to say, what all did you observe? And you're going to say, well, we kind of stayed in the parking lot. We saw the sun come up. We saw the sun go across the sky. And we saw the sun set. In no way do you have the perception that you are on a rock that is spinning, and you don't have the sensation at all that you are moving about 400 and some odd meters per second, faster than the speed of sound. You all have the perception that you all are standing still, the sun is moving around. Now, here is somewhat of a story. If you're like, okay, let's say that I start over here, and I'm going to walk to this side of the room. And I would say, what happened? And you all would go, Burkamp. You know, Emmeline's sitting right there. She's going to say, well, Mr. Burkamp, you walk from one side to the other. Okay. And I would say, no, Emmeline, I didn't move. You actually moved around me. Because if that was the case, if I was actually stationary, and Connor, Hector, okay, Jack, you all are actually spinning, and you're moving around me. I'm not. I'm stationary. You all are moving. You think, oh, no, that's weird. But it's going to be the exact same perception. So to take this leap of faith that says we're on a spinning rock doesn't jive with our observations. You stand outside all day. You have the perception that you are standing still, and this big ball of light is moving across the sky. And we'll get to the moon later, because the moon's going to be a part of the story too. So, the problem is we ran into some issues, okay? One issue is that from a religious perspective, the geocentric model also made sense because of the fact that if you go old school, Old Testament, God made man in his likeness. It made us feel special, okay? Because it's like the ultimate freshman mentality. You have this idea that we're at the center of the universe and everything revolves around us. Literally. I mean, it's just like we're it, okay? God made us in his likeness. We're here. Everything moves around us. And we feel really, really, really special because we're at the center of the universe and everything moves around us. And so if you subscribe to a heliocentric, sun-centered solar system, then we're just like all the other planets moving around the sun. So it's somewhat analogous to you all are seniors, okay? And Peyton, right? Peyton, pay attention. So every day since Peyton has been a little kindergarten, her mom has sent her, packed her lunch, and wrote her a note that says, Peyton, you're special, you're amazing. Every day she opens up this lunch and she gets this message. She feels good about it, okay? All of a sudden, it's her senior year, right? She opens up the lunch, she reads the note that says, I was wrong. You're just like all the other kids, okay? There's nothing special about you. Peyton's gonna be heartbroken. She's going, whoa, 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 whoa. This is bad. Oh, Mom, I'm special. It's like, you're just like all the other kids. That's personal. And that's kind of what happened when you look at a sun-centered solar system. It's just like, whoa, 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 whoa. We're just like all the other planets. They don't revolve around us. Oh, no. Okay, come on. No, we're cool, right? Everything should revolve around us. It doesn't. So this was this big debate. So there were a couple of players in this. One of them was a guy by the name of Nicholas Copernicus. So Copernicus was a Polish monk. And the Catholic Church was a kind of a big hitter in this whole thing. The Catholic Church was very much supportive of the geocentric model. And Copernicus was a monk, kind of worked for the church. And so he was the first one that really came up with a well-reasoned argument for a sun-centered solar system. And so he basically didn't want to mess with everybody. So true story. He wrote this paper, it was beautifully done. And he goes, I don't want this published until after I've passed away. Because he didn't want to mess with it. He goes, after I'm gone, you can have this paper published. So the Copernican solar system was the first real shot and scientific written and well-reasoned paper that supported a sun-centered solar system. Now, so one of the things that they had to deal with was something called retrograde motion. So if you've ever seen these charts, which I find horrible, but it might say like Mercury's in retrograde or Mars is in retrograde or something like that. So let me explain what happens in retrograde motion. So retrograde motion, what happens is that when you look at the planets, okay, and by the way, Wednesday night, if it's clear, I can't remember the exact numbers, but there's like the moon and like 5 planets that are visible, okay? It's going to be really cool if you happen to have a telescope. I'll get back to you on that one. But I know that's going to be coming up. I don't have that right off the top of my head. But when you look at the word planet, planet comes from a Greek word meaning wanderer. So if you look at Venus, Mars, Saturn, all the planets, those appear in different places in the night sky relative to the fixed constellations. So you have the constellations like the belt of Orion, okay? Belt of Orion, if you've never seen that, is like 3 stars. You have the Big Dipper, you have Sagittarius, you have all these different constellations. And so those are fixed places. And what you would see is that you would see the planets, Venus, whatever, they would move relative to those constellations. That's why if you translate the word planet, it means wanderer. Fixed constellations, planets are moving relative to those. So it would be somewhat like me. So if I look right now, okay, and I look out and let's say Connor, okay? So I'm going to look at Connor, and Connor would be in the constellation roller coaster, okay? So I'm looking out, I'm seeing Connor. Connor is just to the right. Imagine that you're here, Connor. That Connor would be just to the right of the constellation roller coaster. Now, Connor gets up and he begins to walk. Oh, Connor's going to move to the constellation Cabinet, and then he's going to move to the constellation Black Tracks, and then he's going to move to the constellation Wooden Doors. So the back of my room is fixed. That's like the stars. And Connor is going to move relative to those points. So I would judge the position of Connor based upon where he is as he moves across the sky. Back of the room is fixed, Connor's going to move. So I would see Connor going in this direction, okay? Now, what happens in retrograde motion, like if you listen to retro music, you listen to old style music. If you dress in retro fashion, you dress in old style clothes. So retro means you're going back in time. So what would happen is that the planets, and it depends on which planet it was, but every once in a while, a planet would reverse course relative to the stars, and it would start drifting to the right. Now, all the planets, all the stars, everything rises in the east and sets in the west. So I don't want you to think that if the planet is in retrograde motion, that it's moving in the opposite direction, like it's rising in the west and setting in the east. That's not what we're saying. What we're saying is that this planet, Connor, for example, would be moving to a certain direction, like to my left. Then he would stop, and then he would move back to the right. So Connor and the constellations are all moving across the night sky. But, and this would take like 3 or 4 months. So what I would see is I would see Connor stop. And then, relative to those constellations, he would start moving backwards. So he would like to move to the constellation Open Cabinet. And then Connor would move back to the constellation Roller Coaster, and then he would move back in the normal direction. So that's what would happen in retrograde motion. So, and this was known. They've known about retrograde motion for literally hundreds of years. The question is, how do you explain it? So if you had a geocentric model, here's the Earth, and let's say here's Mars. So how they would explain retrograde motion is something known as an epicycle. So in an epicycle, Mars would get pulled out of its normal orbit and make a circle around like this, and then it would go back in this normal orbit. And these are known as epicycles, okay? Now, they worked well, okay, on a geocentric model because they had years and years and years of data. It looked horrible. It just didn't feel right, especially when you view this through Newton's laws of motion. It's like, whoa, you're going to tell me a planet is going to go in a normal orbit, then it's going to get pulled out of its normal orbit, make a circle, and then that's going to disappear, and then it's going to go back. And I was like, it worked. They could predict the retrograde motion when it was going to happen, but it was just ugly. It was just convoluted. It's like, there's got to be a simpler way. So that was one of the big problems with an Earth-centered solar system. How do you explain retrograde motion? It's tough. Okay. So the beauty of a heliocentric model is that what would happen is that here's the sun, here's the Earth, and here's Mars. So what would happen here is that Earth is like a race. The Earth is on the inside track. And what happened was that it would catch up to Mars, pass it, and then, so it would, because it's going faster, it would speed up, because it's going faster, it would catch Mars, and then it would go past it. So when that happened, what you would do is you would change the perspective, how you're viewing Mars relative to those background stars. So it was basically an optical illusion. It looked like it was going backwards, but only because the Earth was passing it, and then you changed the perspective against those background stars. So at this point, we're going to fast forward a little bit. So there's two big players we need to talk about. One of those is this guy, Tycho Brahe. So if you look at all the great characters in the history of science, Tycho ranks up there, okay? So Tycho was of Danish nobility, which basically means he didn't have a job. So this is, now you need to understand where we were. So this was before the age of telescopes, okay? So we didn't have telescopes at this point. They hadn't been invented yet. So Tycho had his own island. He was Danish. He was nobility. He had his own island. So what he did is he went out and he built these magnificent machines to track the positions of the planets, the moons, that type of thing. That was his calling. Okay. So, and Tycho did this for decades. So Tycho went out on his island, he built this observatory. Didn't have a telescope, but he had this very complex, I think there might be a picture of it. I thought there was a picture. There's not. But what Tycho did, this is going to be an important part of the story. Tycho had volumes and volumes of books filled with astronomical data. Now, there's a couple of things that Tycho was famous for. One is he had a great handlebar mustache, okay? The Tycho Brahe thing. Cool mustache. The other thing, and you can kind of see this, is that Tycho had a gold nose, okay? So he was the first guy to have bling in your vernacular. So according to the legend, Tycho Brahe got into an argument with another nobleman about how to solve a mathematical problem. Or they took their math pretty serious back then. They didn't have anything else to do. So tempers flared, swords were drawn. Tycho got his nose cut off. So he didn't want to be viewed without a nose, so he had a gold nose fashioned, and that's what you see there. Now, here's what everybody asks. How did he keep it on? Don't know. Could he smell? Don't know. Main point being is he had a gold nose. Now, so that's Tycho Brahe. So Tycho had years and years and years and years and years of data, okay? Now, along comes the next guy. And this is Johannes Kepler. So Kepler was an odd duck. It's the only way to put it. So Kepler believed, number one, in the Copernican solar system. So he believed that we lived in a heliocentric solar or sun-centered system. He also believed that there should be an easy mathematical relationship to describe the motions of the planets. Okay? And so one of his famous quotes was that just as like a songbird is put on earth to sing, I was put on earth to do mathematical calculations. So Kepler in his mind was literally, he was on a mission from God. And his mission was to find the laws to describe the motions of the planets. Okay, and that's pretty important if you think about it. It's like, why are you on earth? My job is to find the mathematical relationship to describe the motions of the planets. Oh, cool. Okay, nice. So Kepler gets hooked up with Tycho Brahe. So this is one of the most intriguing stories in the history of science. And so Tycho knows that he has to have, Kepler knows he has to have Tycho's data. Because he's got to plot the motions of these planets over the periods of years, which we'll talk about in just a second. So he's got to have years and years and years and years and years and years and years of data. He knew Tycho had the best data. So he goes to Tycho's. Yo, Tycho, what's up? They talk. Tycho says, I like you. I understand you're on a mission from God. He's sympathetic to it. And Tycho at this point is up there in years. And he goes, hey, when I die, you can have my data. And this wasn't like information stored on a thumb drive. These were like volumes of books, okay? So, according to the story, it's a good story. I don't care if it's true or not, it's still a good story. So, according to the legend, Tycho passes away. Kepler hears this, knocks on the door, says, sorry to hear that Tycho passed away, my condolences. But he said I could have his data. His family says, Tycho's family, says, really, we want to keep that as a family heirloom. We don't want you to have it. So at this point, Kepler has one of the most greatest moral dilemmas of ever in science. Because on one hand, he's going, man, I'm on a mission from God. I have to find the laws to describe the motions of the planets. Okay, this is important, okay? The other side, he goes, well, they can't have it. I'd have to steal the data. So he's going, gotta have the data. I'm on a mission from God, but then I'd have to steal it. What do I do? So according to the legend, He advances science over ethics. Tycho breaks into the castle, storms the castle wall, kind of does Mission Impossible kind of thing, grabs the books, scurries back to Germany. So at this point, he has Tycho's data. Now let's talk about what Tycho's data look like. So we need to step back for a little bit, and now we need to talk about the moon. What does the moon have to do with this? The moon has everything to do with this. So here's the sun, and here's our rock, and here's the moon. Now, this is looking down on top, okay? This is important. So this view is that you're looking down and you're seeing the North Pole. Now, the first thing we need to establish is that the Earth spins counterclockwise. And I know the Earth spins counterclockwise because if I'm here in Mesoamerica and the camera, or Emmeline is the sun. Let's go with that. So if I'm here, okay, Emmeline, this is noon. Emmeline is directly overhead. If I'm over here on the opposite side of it, this is midnight. I'm on the opposite side. So I know that we spin counterclockwise because as the Earth comes around like this, if I come around like this, okay, I'm looking towards the East Coast. That's where I'm at, right? Okay, I'm in DC right now. So you all would look towards, oh, where's Burkamp? Oh, he's in the East Coast. Okay. So that's the direction that I'm in. So that's why when we come around like this, the Earth is spinning counterclockwise. You're going to see the sun rise in the eastern horizon. Then we're going to come around like this. We're going to hit noon. We get over here. We're going to look towards the west coast, and we're going to see the sun setting. So this is how we know the Earth spins counterclockwise. So here we are in the North Pole. This is looking down from on top. So here's this shadow line. So if you're right here, that's 12 o'clock noon. Sun, boom, directly overhead. If you're over here, okay, if you're over here, this is midnight, okay? You're on the opposite side of the sun. That's going to be midnight. If you're here, that's going to be, as you're coming around like that, that's going to be sunset. And if you're here, that's going to be sunrise, okay? So imagine this, okay? Here's the Earth, okay? Here's the sun. Here's the shadow line. So if you're this little spot right here, if you're here, that's noon. As this comes around like this, you're going to see the sun set. You come around like this, midnight, come around like this, boom, sunrise. Now, let's talk about the moon. On a full moon, okay? On a full moon, the moon is over here on the opposite side of the Earth. So this is why you can see, when you have a full moon, you can see the full surface of the moon. Now, this is going to be important. A full moon is going to rise at sunset, okay? Hold on. I got to take a phone call. Stand up, take a stretch. I'm going to take a stretch. We'll continue this story in just a second. Okay, sorry about that. Had to take a phone call. All right, so here's the drill. So if you can model the moon, and when you can see the moon in its phases, you can use that as a model for the planets as well. So here's what's going to be important. When it's a full moon, and we say that the Earth, the sun, and the moon are what we call in opposition. They're all in a straight line. So when a planet is in line with the Earth, and it's one of the exterior planets, Mars, Jupiter, Saturn, whatever, you can see a full Mars. You can see a full Saturn, Jupiter, because they're all on the outside. So when this happens, so you know when you're looking at a full moon, a full Mars, whatever that is, as this spins around, you're going to see that planet or the moon rising at sunset. When you're seeing the sun go down, you're going to see this planet come up. Then at midnight, it's going to be directly overhead. then when you get over here to sunset, this is when you're going to see a full moon set, and you're going to see the sunrise. Now, if the moon is here, okay, so let's say the moon is here, okay, here's the shadow. Now, if the moon is here, you're going to come around like this, and at noon, the sun's going to be directly overhead, and then you would be able to see, that's when you'd first be able to see the moon. So this is why sometimes you can see the moon during the daylight. Because then as this comes around at sunset, you would see a quarter of the moon, and it would be directly overhead. And then when you get over here, you'd see the sun, you'd see at midnight, you'd see the moon setting. Because then you wouldn't be able to see it anymore once you get over here. If the moon is up here, okay, at this point, then you'd see it rise at midnight, you'd see it set at noon, and then when the sun's coming up, the moon would be directly overhead. So depending upon where the moon is, that's when you, and how much of it you can see, you can get an idea of where the moon is in its orbit. Now, we have two interior planets, Venus and Mercury. So, here's the problem. We can never see a full Mercury or Venus. Here's the reason why. Let's say, for example, Mercury and Venus are here. Well, there's two reasons why we can't see them. Number one, you'd be looking at the sun, small problem. Number two, you'd be looking at the dark side of these planets, okay? Because even if you can see them, you're seeing the dark side of them, you're seeing the shadow side. Now, if they were over here, on the opposite side of the sun, same problem. The sun's in the way. Oh, no, we can't see them there. So this is why Venus and Mercury are known as the morning and evening planets. So the only time we can see Mercury and Venus are basically when they are here and here in their orbit. Because when they're here, this is why we call them sunrise and sunset planets. So if Mercury and Venus here, and this is where Venus is, by the way. If you go out tonight, I don't know if the weather's going to be in Wichita, Kansas, but if it's clear tonight or any night this week, you can look to the west and you'll see a very, 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 very bright object, and that's going to be Venus. So Venus is here in its orbit. So you're coming around like this. Here you are at sunset. So you're going to come around like this. Excuse me, I'm sorry. It's over here. It's in the evening. Mercury and Venus are here in its orbit. So you're coming around here like sunset. Okay, this is coming around. So you would see the sunset, and then you could still look and see this way. You can still see Venus. So Venus is on this side of the sun at this point. So whenever you see planets in the western sky just after sunset, that means that they're somewhere on this line of sight. Might be Jupiter, might be Saturn, whatever. So any planets that are visible after sunset are in this portion of the sky. Now, if you see planets at midnight and they're overhead, oh, that means they're out there. So this is what you can do. And this could backfire, by the way. So let's say you're going to go to prom. You leave the cotillion, where prom is this year, and let's say it's midnight. Now, this could backfire, so just be careful. So let's say you want to test the knowledge of your date. So it's midnight. You look straight up. It's midnight. You look straight up. You pick a bright star. And you go, oh, look, there's Venus. Okay? Now, if your date goes, oh, yeah, that's cool. Your date has no concept of where the planets are in relation to the Earth. Okay? Because at midnight, you put your point straight up here, there's no way you could be Venus or Mercury. Now, here's the problem. If your date has had me for physics, and you do that, your date's going to look and go, you're an idiot. There is no way that's Mercury or Venus at midnight. Okay? You're a schmuck. So, just be very careful. I'm just telling you. Okay? So, ladies, gentlemen, I'm just telling you. If you go to prom and you're going to pull the Burkamp, oh, look, it's Venus line at midnight, be careful. Just saying. You don't have to, but if you do. Now, if Mercury and Venus are over here, then then they're going to be visible just before sunset. Because if they're here, you're coming around like this, boom, there you go. Now, with all of that said, here's where it all comes together. Tycho has passed. Kepler has his data. Kepler's gone back. He goes, look, I'm trying to find these laws of planetary motion. Kepler wages war on Mars. And he picks Mars because, let me kind of clear this up. There's the sun, here's the Earth, here's Mars. So Mars is the closest exterior planet to the Earth. So he has a lot of good data on Mars. Now, but here's the problem. You have to look at what all Kepler had to sort out. So, number one, the Earth is tilted on its axis, okay, which is a good thing. Okay, I'm not saying that's a bad thing, but the Earth is tilted on its axis. Okay, so we're like this. So the Earth is spinning and we're tilted. We're moving all the time. Mars is moving all the time. There's no fixed points. The only thing you have is the fixed point in space. Now, here's the problem with that. Let's say here's the Earth, here's Mars. They're in opposition. You're looking at a full Mars, and you're on Earth, and you're judging the position relative to a particular constellation. Cool. Now, a year later, Earth comes back to that same point. A year later, Earth is back to its same point. Now, Mars might be over here. So now, when you're looking at where Mars is, even though it's 1 year on the Earth, the perspective of Mars is going to change drastically. Or even worse, Mars gets back to the same point. Earth might be here. Now, even though Mars is back to its same point in its orbit, you're looking at it this way, and it's going to completely change that perception about where Mars is located. So this is why Kepler had to have years and years and years of data. This is why he stole the data from Tycho Brahe. So he came up with 3 laws. These aren't suggestions, these are laws. So the first law is the law of ellipses. Okay? And this is this graph right here. So if you remember your days in mathematics, an ellipse has 2 foci. So one foci is located at the sun. The other foci is some point out in space. This created controversy. And you would think, why is this controversial? Here's the reason why. The circle was viewed as the perfect geometric shape. Okay? Absolutely perfect geometric shape. That's what it's viewed as. Perfect geometric shape. So when Kepler comes along and says the planets move in ellipses, the heavens were viewed as the realm of God. And the heavens should be moving in perfectly geometric shapes. So for Kepler to come along and say, oh, it's moving in an ellipse, it's just like, hey, God made a mistake. He tried for a circle, he was off by a little bit, he made an ellipse. It's like, oh, really? Bit of controversy. Moving in ellipses. Now, the second one is called the law of equal areas and equal times. So we'll spend an entire lab on this tomorrow. So what happens here, here's the sun, here's the orbit. And so in a certain amount of time, it might be like 30 days. So in a 30-day time period, if you were to draw a line from the sun to the edge of the orbit here, and from the sun 30 days later to the edge of the orbit here, you can calculate this area, like the area of the circle. Now, out here, in that same 30-day period, when it's further from the sun, this area here is the same as this area here is. Now, here's the problem. This has a much greater arc length, if you remember your days in geometry. This has a much bigger radius. This has a shorter radius. So the only way these 2 areas can be the same is if you're going faster when you have a smaller radius, and you are going slower when you have a bigger radius. So what that means is the planets are not traveling at the same speed all the time. So here's all I want you to remember for now. When it's closest, that's when you're going faster. When you're further away, that's when you're going slower. Okay? Got that? Small inverse relationship. Small radius, big velocity, big radius, slower velocity. Equal areas and equal times. Now, here's the problem. If you've ever looked at the planets, it isn't like you look out and you see Mars and there's like an edge to its orbit. Kepler had to establish the edge of this orbit. Now, the other thing that he didn't know is the actual distances, and this is going to play out in the third law. Kepler was doing all these calculations late 1600s. No calculators, no Siri, no calculators. Didn't even know that he was working off the right model of the universe. So, if you're doing these calculations, okay, Carson, you're the calculator queen, okay? God bless you for that. And let's say that you're trying to do these without a calculator. I'm Kepler and I don't have Carson with a calculator. My favorite number to use is going to be the numeric value of 1, because that's simple. So what Kepler did, he says, okay, I don't know the distance from the Earth to the sun. He used that as the reference point. So he says, okay, here's the sun, here's the orbit of the Earth. I'm going to let that be 1 AU. And that AU stands for an astronomical unit. Okay? Just remember it's AU. It's an astronomical unit. So Kepler said, okay, I'm going to let that be the distance from the sun to the Earth. He didn't know the actual distances. He couldn't Google it. He couldn't ask his phone. No one knew the actual distance. He says, okay, I'm just going to let this be a numeric value of 1. Then, he knew the Earth took a certain amount of time to orbit around. He let that, oddly enough, be 1 year. He could let it be 365 days, but that's going to be awfully complicated because he doesn't have Carson with a calculator. So he says, okay, we're going to let this be 1 year. Now, his third law is what's known as the law of harmony. And this is what's written down here at the bottom of this front page. And this is what's on your equation sheet. So it says, period of A squared over period of B squared equals RA cubed over RB cubed. Now, listen to me. This is the only time. Listen to me, listen to me. Tyler, listen to me, okay? Jaden, listen to me. It's the only time this is going to happen. I don't care what the units are. This is a ratio. The periods could be in years, days, hours, doesn't make any difference. The radius could be in astronomical units, kilometers, inches, centimeters, doesn't make any difference. Okay? Because it's a ratio. It is a ratio. Doesn't matter what the units are. But here's what's important. This equation, and you'll see later on why this works once we get into Kepler's laws. Once we get into Newton's laws of motion. These can only be used if they orbit the same center. Like I could use this for the Earth and I could use this for Mars. So I could say, okay, hey, here's the Earth, here's Mars. I could do that because Earth and Mars both orbit the sun. You can look at the Galilean moons of Jupiter, okay, named after Galileo, oddly enough. Io, Europa, Ganymede, and Callisto. Those 4 moons orbit the planet Jupiter. I could use that to compare the period and radius for those 4 moons. What I could not do is I could not compare a moon of Jupiter to our moon, because our moon orbits our Earth. Those moons orbit Jupiter. So this works, and it works beautifully. But they have to orbit the same center, okay? Doesn't make any difference what the center is. They both have to orbit the same center. Now, let me give you a simple example. And I'm not sure how we're doing for time, but stay with me here. So let's say we want to say, here's the sun, here's Mars, here's Earth, okay? So we could say, okay, period of Mars squared over the period of the Earth squared equals the radius of Mars cubed over the radius of Earth cubed. Now, squareds and cubes. Mind you, Kepler is doing this without Carson. He has no calculator. You have 4 variables. Period of Mars, period of the Earth, radius of Mars, radius of Earth. Now, what I'm going to do is I'm going to cross multiply. Okay? Just do a simple cross multiplication. So I'm going to have the period of Mars squared times the radius of Earth cubed equals the period of Earth squared times the radius of Mars cubed. This is more functional than as a ratio. Cross multiply. Functionally, it makes it easier to do. Now, if you're Kepler and you don't have a Carson, you're going to try and use the numeric value 1 every chance that you get. So what Kepler did, he says, look, I'm going to let the period of the Earth be 1 year. There you go. I'm going to let that be 1 year. I'm going to let the radius of the Earth be 1 astronomical unit. So I'm going to let the period of the Earth be 1 year. I could use 365 days, but I don't have Carson. I don't know the radius of the Earth, so I don't know what to do there, so I'm just going to let that be a value of 1. Okay? Because this is a ratio. He didn't know the distances. He's just trying to find the math. So look what happens. This is where the magic happens. We're going to let the radius of the Earth be 1 astronomical unit. We're going to let the period of the Earth be 1 year. Now, those numbers are still technically there. But the cool thing is that those aren't zeros. They're just ones. So what that leaves me with is the period of Mars squared equals the radius of Mars cubed. Okay? The other values are there. They just have a numeric value of 1. And that's what Tycho was trying to do. Excuse me, what that was Kepler was trying to do. So let's say that you know that the period of Mars is, 2.8 years. I'm just going to make up a number. So we know Mars takes 2.8 years to go around, whereas it only takes the Earth 1. And we want to find the radius of Mars. So what we're going to do, I'm going to try and find the radius of Mars. So I'm going to take the period of Mars squared, and then I'm going to take the cubed root of that value. Now, you're doing this, you're Kepler, and you're doing this without a calculator. So you're going to take the cube root of 2.8 squared. So I have a calculator here. Carson, sorry, I'm going to do this on my own. So I'm going to take 2.8, and I'm going to square that. Okay? And then I'm going to take the cube root. So when you do the cube root, some calculators have like actual cube root functions. The other thing that you could do is you have like a caret, and you can go either 0.333 and punch in a bunch of numbers, or you can do the caret and raise it to the fraction of 1/3. I'm old school. I'm just going to go raise that to 0.333, and I get 1.99. Okay? So, oh, go away. Whoa, I got all sorts of weird stuff going. So if I do this, I get about 2. Okay? So what that tells me is that if Mercury has a period of 2.8 years, that means that works out to be astronomical units, and that's going to be twice as far. So what that tells me is these were, and I just made these up. So what that tells me is that Mercury is twice as far, Mars is twice as far from the Earth, from the Sun, as the Earth is, because it's 2 astronomical units. Okay, so what you're going to have is, hold on, I'll get it again. This assignment, okay, collection of Kepler's questions. So you got some questions to answer here. You want to use the numeric value of 1 every chance that you get. So when you get to, like, for example, number 7, Venus has a period of revolution of 225 Earth days. Find the distance between the Sun and Venus in astronomical units. So you have 4 variables. For example, on this one, on all of these, you're going to have 4 variables. Set them up. So you're going to have period of the Earth, period of Venus, radius of the Earth, radius of Venus. When in doubt, you could just work in days. You could let Venus be 225 days, and then you would let the Earth be 365 days. If you don't like that, take 225 days to get the period of Venus in years. You can take 225, divide that by 365, that's going to get you a decimal, okay? Venus is inside our orbit. Clearly our radius has to be less than 1. So what you could do is take 225, divide that by 365, get a decimal, and then plug that into a situation like this, where you'd have the period of Venus squared equals the radius of Venus cubed. And if you can do that, but you'd have to let the radius of the Earth be 1 astronomical unit and the period of Venus, or the period of the Earth be 1. Okay, I realize this was less than ideal, but it's the best I can do. I don't know the outcome because I'm forming this on Friday. Hopefully this might be purple, which indicates that the K-State is in the Final Four. If it doesn't, well, it kind of matches my shirt. How about that? Okay, good luck, and I will talk to you all tomorrow morning.